We're going to be finding the reaction rate per area of catalyst using the Stefan-Maxwell equation. And in this scenario, we're going to have ethanol reacting to form acetaldehyde and hydrogen on a catalytic surface. So we have our ethanol, C2H6O. That's going to be in gas form, and it's reacting to create acetaldehyde and hydrogen. Oh, that's not water. So we have a catalytic surface in which this occurs, and our ethanol is going down onto the catalytic surface. Ethanol is our first component, and we'll say acetaldehyde is our second, and hydrogen is our third. So we have our ethanol reacting on a catalytic surface, and coming up is our acetaldehyde and our hydrogen. So we have 1, 2, and 3. This is our catalytic surface. We have some information here about our pressure and our reaction rate. So our pressure is going to be equal to 101.3 kilopascals. Our temperature, we're also given that, is 548 Kelvin, and our reaction rate is 10 moles per meter squared second mole fraction. With these variables, we're also given our diffusion coefficients, so B12 is equal millimeters squared per second. Our diffusion coefficient from the ethanol to the hydrogen is equal to 230 millimeters squared per second, and our final diffusion coefficient from our acetaldehyde and our hydrogen is for 230 millimeters squared per second. It's a good practice to put everything in the units that you're going to want to use. So what that means is that these millimeters squared per second, I'm going to transform into meters squared per second. It's just easier to use that way. So that's going to be 72 times 10 to the 6th meters squared per second, 230 times 10 to the 6th, and 230 times 10 to the 6th again. And we also have some more information that we can put down. So right above our catalytic surface, we have a bulk, which no reaction is occurring there, and we have mole fraction. Oh, that's not a box. We have a mole fraction for each of our components. That's also not a rectangle. Why am I so bad at drawing a rectangle? Okay, there we go. So this is our bulk. And our mole fraction for each component is for our first component is 0.6, our second is 0.2, and our third is also 0.2. Our thickness from the catalytic surface to the bulk, now that has a number as well, so our thickness is equal to 1 millimeter, which we want to put it in meters, so that's going to be 1 times 10 to the negative third meters. And then we're going to be working in changing positions, so that's going to be our z direction, and so we'll just assume that this is the positive z direction. From here, let's start with our Stefan-Maxwell equation. So we have all the information that we really need, and for our Stefan-Maxwell equation, or Maxwell-Stefan, some people say it the other way around, we have our driving force is equal to our change in mole fraction over our change in position, and that's going to be equal to the sum J of our mole fraction of I multiplied by our molar flux of J over our concentration times our diffusion coefficient of Ij, and that's, yeah. And up here, there's also, you're going to subtract our mole fraction of J multiplied by our molar flux of I. Move that to the middle. There we go. Now we can write our Stefan-Maxwell equation for each of our components. We'll do one for our ethanol and one for our acetaldehyde. We don't do one for hydrogen because what you can do is you know that our mole fraction is y1 plus y2 plus y3 equals 1. So you can just take your final Stefan-Maxwell equations and subtract them from 1 and find your y3 or component 3 or whichever component you're looking for. So we'll start with our acetone. Or sorry, our ethanol, not our acetone. So our ethanol, that's going to be the driving force of y1 or mole fraction of 1. Or let me rephrase this. It's going to be the change in our mole fraction of 1 over the change in position is equal to the sum of 2 and I'll have a mole fraction of 1 multiplied by molar flux of 2. And again, 2 is your acetaldehyde and 3 is your hydrogen. Minus mole fraction of 2 multiplied by our molar flux of 1 all over our concentration multiplied by our diffusive coefficient of 1, 2. And we can also do our acetaldehyde. It's going to be along the same lines. We just switch out some of the numbers. So instead of y1, it'll be y2 equals our mole fraction of 1. Oh, sorry. I need to add something as well. So for ethanol, you have your change in your from 1 to 2, but you also have your change from 1 to 3. So you have to subtract this as well. So you have your mole fraction of 1, your molar flux of 3 minus your mole fraction of 3 multiplied by your molar flux of 1 all over your concentration and your diffusive coefficient from 1 to 3. Now we can go on to our acetaldehyde, and it's going to follow the same sort of idea. So you'll have your mole fraction of 2 multiplied by your mole flux of 1 minus mole fraction of 1, 2 over C 1, 2 minus mole fraction of 2 molar flux of 3 minus mole fraction of 3 molar flux of 2 over a concentration from 1 to 2 to 3. All right. Now we don't have Z. We know the thickness though. So what we can do is we can create a variable N, and this is equal to our Z value, our position divided by our thickness. So the change, that means the change in N is equal to the change in our position over thickness. Therefore, our change in position is equal to our change in N multiplied by thickness. So we can say that we take this right here. We want to change that into our change in the molar fraction of I over mole fraction, the change in N. And so that's going to be equivalent to a change in mole fraction of I divided by the change in dz multiplied by dz over the change in N. And now we can plug that in to both of our equations, both of our Stefan-Maxwell equations we created for ethanol and acetaldehyde. Get rid of the sum, because we're doing the sum. We don't need that. This sigma in there. So now we change our Stefan-Maxwell equations. So this should be the change in y1 over the change in N is equal to the thickness multiplied by this entire part of the equation. Bam. Same idea goes here. N is thickness multiplied by this. I'm going to end up solving this entire problem in Excel, but what we want to do is make an estimation of what our molar fraction, our molar flux of component 1, our ethanol. And so to do that, we have to understand that our concentration is equal to our pressure over our R constant multiplied by our temperature. And that's the first part that we have to know. The second part is that this part of the equation and all these mole fractions are somewhat equivalent to 1, based on the order of magnitude. So now we just have our molar flux and our thickness, our concentration, and our diffusive coefficient. And we can get that our molar flux component 1 is equal to our concentration multiplied by the diffusive coefficient divided by our thickness, yeah. And this is because P over RT equals concentration, we can put in that this also equals pressure multiplied by our diffusive coefficient over RT thickness. We're also looking at the reaction rate, and that is the relationship between our mole fraction and our molar flux. So like our mole fraction of the reaction rate has to be the initial starting material, right? So we have our mole fraction of 1 multiplied by our molar flux of 1, and that's going to be equal to our reaction rate. So our mole fraction is equal to our reaction rate divided by our molar flux. I'm sorry, this is going to be actually your molar flux divided by your reaction rate. And we have our components 2 and 3, which are the products, so they're not necessarily related to our reaction rate. So we can just say that our component, mole fraction of component 2 is equal to 0.25. And so we can find our mole fraction of 3 based on 1 minus component 2 minus our component 1. And now let's move on to Excel to find the final reaction rate per area of catalyst. Here we have our Excel sheet, and I've already input all of the data that we previously knew about each of the parts of our problem. So we have, oh, that's not right. That should be the same. Same one. Oh, and get rid of one more 0. Those two are the same. All right. This is here. Let me just, it is 230e to the 6th. Yeah, okay. Okay. So we have our diffusive coefficients. We have our pressure, our time, our value, and our concentration. And remember that I found this concentration by doing our pressure divided by our R value multiplied by our temperature. And that got me 22.2, but there's there. So 22.2. I'm gonna do some rounding, and here's our bulk mole fractions for each of the components. Here's the mole fractions that we want to find. Here's our distance, which is our thickness, which is 0.001. Here's our reaction rate, which is 10, and then right here we have our molar flux, which we're going to calculate in just a few seconds in Excel. You should know that because the reaction is a 1-to-1-to-1 ratio, right? You have 1 ethanol transforming into 1 acetaldehyde to 1 hydrogen. That means that our our negative, I should say N2 equals N3 is equal to negative N1, right? Because it's going back to the product versus the initial starting point. So our N1, that's going to be equal to, we have our pressure, and I'm going to put parentheses around this actually. So we have our pressure multiplied by our diffusion coefficient of 1 to 2 divided by our R value multiplied by our temperature and our thickness. All right, so that's our first estimate. All right, let's just double check that. So we have our pressure. All right, yep, and yes, okay. And this is actually going to be negative, right? Because our N1 is negative compared to N2 and N3, but our N3 is negative of this, so it's positive, right? And there we go. Now for our mole fractions, we know that our mole fractions are equal to our N1 divided by our reaction rate. Here's our reaction rate. Oh, just this one. Thank you. Oh my gosh. There we go. Here's our y2 is 0.5 and y3 is 1 minus 0.5 minus our y2. There we go. So now we're going to find our reaction rate. All right, so we're going to have values ranging from, let's start at 0, and we're going to go all the way to 1,000. So use fill, do series, go from 1 to 1,000. And we'll do by column, not by row. And there we go. Now we have our DZ, so our change in position, our mole fraction of 1, our mole fraction of 2, our mole fraction of 3, and then we're going to have our mole fraction of 1 divided by, or our change in mole fraction 1 divided by our change in N, or N. So this is going to be equal to, our change of position is going to be equal to our D value divided by 1,000, because we have 1,000 points, and multiply that by the position right here. Oh my gosh. Okay. Oh my gosh. And so, oh, let me put in that there. Yeah, there we go. Okay, now it should be good. There we go. So if we scroll all the way down, the last value should be equal to our D value, which is 0.001. Perfect. All right, so our Y1 value is given to us right here. Bam. Our Y2 value is given to us right here. Wait, we just calculated these. And our Y3 value. Perfect. So now we're going to use our Stefan-Maxwell equation to find our change in, or our driving force. We're essentially going to find our driving force. And I'm looking at the equation right now. So the first thing we have is you're not going to multiply it by the thickness. That's going to be right here, right? So first thing we have is our, let's see, this is for the ethanol. We have our mole fraction of 1 multiplied by our molar flux of 1. Bam. And that is going to be, this is going to subtract from that mole fraction of 2 multiplied by our molar flux. I'm looking at the wrong one. Oh my gosh. Okay, let me go back. So we have our mole fraction of 1 multiplied by our molar flux of 2 minus, subtract from that, mole fraction of 2 multiplied by our molar flux of 1, and then divide this whole thing by our concentration multiplied by our diffusive coefficient. So concentration multiplied by our diffusive coefficient of 1 to 2. And let me just check. So divide by that. And then we're gonna subtract from that, and we're gonna have subtract from that y1 multiplied by our molar flux of 3 minus y3 multiplied by our molar flux of 1 divided by our concentration multiplied by our diffusive coefficient of 1 to 3. All right, so there's our first one, and then let's do the change in our second. And this is, again, kind of the same concept. Instead, you're using your mole fraction of 1 multiplied by your molar flux of 1 minus your mole fraction of 1 multiplied, oh, let me put parentheses there, mole fraction of 1 multiplied by your molar flux of 2 divided by your concentration multiplied by your diffusive coefficient of 1 to 2, and subtract from that mole fraction of 2 multiplied by mole fraction of 2 multiplied by your molar flux of 3 minus your mole fraction of 3 multiplied by your molar flux of 2 divided by your concentration, which is multiplied by your diffusive coefficient of 2 to 3. All right, there we have our Stefan-Maxwell equation for our first component and our second component. So now we can find our mole fraction, and that's going to be where you were plus where you are multiplied by your Maxwell-Stefan equation. It's going to be the same thing for our Y2, where you were plus where you are multiplied by your Maxwell-Stefan equation. And this should still be, okay, well, let me do, there should be 1 minus, hello, 2 minus 1. There we go. And I can just drag that all the way down. It'll change in a second. So let me make sure. I think that should be fine. Yeah. And obviously these values aren't quite correct, so we'll change them in a second. But you get the idea. I think something went wrong over here. I'll change that out. See what that is. And then these values, you got to make sure that you put dollar signs in front of the values you don't want to change. So we do want that to change. We don't want our end value to change. We do want our mole fraction to change. We don't want our other end value to change, and our concentration should remain the same, and our diffusive coefficient. So again, with this one, our molar flux does not change, nor our concentration or our diffusive coefficient. All right, same thing for this one. Concentration stays the same, diffusive coefficient stays the same. Molar flux stays the same. Well, we'll change that in a second, but that's going to be changed by a solver, not by. So you can drag that all the way down, that all the way down. And now these values look a little odd, I'm not going to lie. So I'm going to see what's up with that. Yeah, that's not right. All right, so basically what I did wrong is I just put the diffusion coefficients in incorrectly. I made it. I made a big mistake. So the Maxwell-Stefan equation, Stefan-Maxwell equation, whatever you want to call it, you're supposed to add each part together, not subtract it. That makes a lot of sense, doesn't it? It's a sum, right? So what you're going to want to do is in the original equation, I have it right here. Camera's right here. You see how I said to subtract it? You're going to add it. So that's added. And that should get you the correct answer. So from here, we look at our bulk quantities. And we want our bulk quantities to be equivalent to 0.6, 0.2, and 0.2. And they're not, as you can see. So what we're going to do is we're going to take the sum squared of each one of them and then use a solver in order to change our surface values so that we can make that true. So this is G1002, H1002, and I1002. This should be 0.6. This should be 0.2, and this should be 0.2, but it's not. So we're going to do this minus our actual value squared. Squared. How do I? Same thing with this. I think I can just write it down. Now we have our sum squared value, which is going to be the sum squared of our two numbers we got right here. We're not going to do the third value because we don't really need it. We're just going to do 1 minus y1 minus y2, and that'll get us our third molar fraction. So this is our sum squared value, and it's not exactly what we want it to be, right? Yeah, it's not exactly what we want it to be. So we can take our solver, and we can change it to the smallest value possible by changing these two cells. Don't have to change the third one, that will change automatically. And if we solve for that, hopefully it'll work this time. Come on. Yeah, we'll keep that. All right, so what we have here is our sum squared value is almost equivalent to 0, which is wonderful. And our values right here are almost equivalent to, this one's almost 0.6, this one's almost 0.2, and this one's almost 0.2. It's essentially there. And our y values on our surface have changed. So let's see what they changed to. So those are our mole fractions that are actually true. So our surface values are equivalent to 0.5, 0.3, and 0.2. And now we're going to try to find the reaction rate per area of catalyst, right? We said we were going to do that originally, so let's do that now. So now we have the mole fraction of the surface for all of our components. So we can take our mole fraction, relate it to our molar flux, and relate it to our reaction rate, and that's how we can find the reaction rate per area of catalyst. So we're going to take our molar flux and we're actually going to change it up a little bit. We're going to take our Y1, multiply it by our reaction rate. Oh, equals that multiplied by our reaction rate. We get these values, right? And you'll notice a lot of negative ones. So our sum square value has also changed. You can minimize that if you'd like. I think it's the same. Okay. So our you notice that in diffusion equations like this, the catalytic surface will actually use a lot of the energy. So when you have something, an Excel sheet that looks like this with a lot of -1 values and 1 values, what it's telling you is that the reaction rate is actually too high. The catalytic surface is taking the reactants and just popping out the products, but it's going so fast that it's not able to do it very well. So there's a couple ways that you can change this, and one of them is to change your reaction rate. The other is to change the thickness. And there's another scenario in which you realize that your catalytic surface is not actually a good catalyst, then you should change it to something else. But if you change your reaction rate to something extremely small, and you'll see that the numbers are already back to something that's more plausible. And then if you change your your distance, it also does the same thing, right? So it changes it to something more plausible. Change this back. But right. So you 0.00101. Yay! And then you'll also notice that sometimes your mole fraction for 1 will be quite high, and that means that your catalytic surface is also not producing the products very well, right? Because you have a very high amount of reactant still left to be reacted with. So also talking about the catalytic surface, you'll notice that if you change, okay, so let's just change this to a very, I'm trying to get, I guess that's good enough. You'll see here that your values for your surface and your bulk are basically the same, and that's telling me that the catalytic surface is again not reacting fast enough because your bulk and your surface is at the same mole fraction, right? There's no change, nothing's been produced or, reversed. And so you have to change your film thickness once again, or your reaction rate to, I don't know if it's something possibly larger. Right, so you put it to 10, that's still pretty high. But you make your distance like 0.00. Yeah, basically this changes it again. I mean, this shows us that it's being eaten up. Now if we change to something along the lines of 0.003 and 0.0001. I'm trying to get a negative number in our bulk phase. Let me just, maybe it's this. Let's just do 10 negative 20. Why is it still not? Okay. Goes 10 to the let's put these back to the originals, and then we'll change our n values back to what they originally were, which was it was our d multiplied by our diffusion, so d2 divided by r C thickness. All right. So also, and then let's make this negative. So you can also see that if we change this to something. All right, give me a second. So this is the reaction rate divided by, or the reaction rate multiplied by R YS. Okay. All right, here we go. So right here, our final products, you'll see that our component of 1 is in the negatives and our component is in the positives at the beginning. So what that's telling me is that our components are being eaten up extremely quickly by the catalytic surface and being thrown into a product. And so again, that you might have to change your catalytic surface for that so it doesn't do that and you're not eating up all your reactant. And another thing you could do is, again, decrease the reaction rate. So if we decrease the reaction rate even more, the distance. Right, see, the distance did make difference. The film thickness did make a difference. And so now it's in the positives. This might be increase actually. Oh yeah. Let me do divided by or multiplied by R, these values. Yeah, so there you go. So it's in the positives. If I make this very small again, I might go back into the negatives, but basically what's happening is, again, the catalytic surface, if this is in the negatives, the catalytic surface is eating up your reactant very quickly and spitting it out as a product and using it all up. So again, change your catalytic surface, change the film thickness, make it smaller, and then change your reaction rate. So there's a couple things you can do, right? So let's go over everything again. If your bulk surface is the same as if your bulk mole fraction is the same as your surface mole fractions, you want to change the reaction rate and your film thickness, or the catalytic surface isn't like a catalyst. It's not eating anything up, right? Because the mole fractions are the same. There's no reactant turning into product. If the reactant is in the negatives, you might want to change the catalytic surface once again. It's eating up the reactant extremely quickly and turning it into a product extremely fast. And the reaction rate could also be changed to something smaller so it doesn't eat up the reactant as fast. Or the film thickness could be changed, and that will make your mole fraction of your reactant in the positives. I mean, if you really want to go into it, catalytic surface could be changed by a chemical engineer. They work with those materials, the reaction rate is something more chemists deals with.